Good day. For our OSLab project, we've created a memory placement simulation program. As you can see, we've implemented the entire program in Python. We chose Google Colab as allowed by the project requirements as our development and hosting environment. Here in cell 3 is our complete source code. To ensure our program adheres to correct programming styles, we've structured it in an object-oriented way. The code is built around two main classes, a simple process class, which acts as a data structure, and the main memory simulator class. The memory simulator class manages everything. The memory map, all the processes in their different states, waiting, active, or finished, and all the core logic for the simulation clock, or as we call it here, a tick. I will briefly scroll through the memory simulator class for the def init and def tick functions for you to see. All right, now for the user interface requirement, we used Streamlit to create an interactive web application. This provides a clean and structured way for a user to interact with our simulation. I will now run the cells here, which would launch the Streamlit app in the background and uses ngrok to create a secure public URL. Let's wait for a second for it to appear under the source code cell, and then click on the first link here just before the localhost. As you can see, here is our application's user interface. It's designed to be clean, interactive, and easy to navigate. As you can see, we've explicitly stated the allocation algorithm we chose, which is first fit. On the sidebar, we have all the user inputs required by the project. A user can set the total memory size, the time cost for compaction or the SC, and the time cost for coalescing whole or the CH. We also have full functionality for defining the processes. We can set the number of processes, and for each process, we can individually define its size and its required time unit. This interface fully meets the functionality requirements, allowing us to test any combination of inputs. So to begin our analysis, we will perform two runs. For the first run, we will establish a baseline using low overhead costs. I will set the compaction cost of the SC to 10 and the coalescing cost to 2 as seen here by default. Next, we will use these five processes with their defined sizes and times by default as is. And now let's run the simulation. As you can see, our program provides two clear outputs as required. First, the most important result, the final time unit, which is 35. Now let's look at the memory state at its busiest point. The chart shows P1, P3, P4, and P5. You'll notice that process 2 is missing. This is the key to the simulation. So if we look at the log, we can see what happened. At time 1, P1, P2, P3, and P4 were loaded. P5 tried to load but failed, and compaction wasn't useful yet. So at this moment, the busiest state was for processes, including P2. But then at time 6, the short running P2 finished and released its memory. This is the critical event. The system tried to load P5 again, but the holes were still fragmented. This failure triggered compaction. The system paid the 10 unit SC cost, which jumped the clock to time 18. This compaction combined P2's free space with the final hole, creating a new 400 unit hole. So at time 18, as we can see here, P5 was finally allocated. This created a new busy state of four processes, P1, P3, P4, and P5. Our program is smart enough to show this more interesting post-compaction state. This chart is a perfect visual of why compaction is necessary. P2 had to finish to make room for P5. Finally, for a complete breakdown, we have the full simulation log. So this log outputs every single action the simulator took. Every tick, every allocation attempt, every process completion, and every time the OS performed a coalesce or compaction. This ensures our results are verifiable. So now we will fulfill the final and most important requirement, running the simulation again, changing only the SC and CH variables this time to observe the impact. So we will keep all five processes as is and the 1000 memory size exactly the same. But for the second run, we will simulate a slower or a more expensive system. I will set the compaction cost here to 50, and then I'll also set the coalescing cost to 10, and then run the simulation again. As you can see with the difference here, the final time unit is now 91. So this is our final observation. The process and memory were identical, but the total time jumped from 35 to 91. This is because compaction and coalescing are system overhead. They are not free actions, they are tasks that consume system time, which our simulator correctly adds to the global clock. In the first run, every time a process finished, the cost to check for holes was only 2 time units. In the second run here, that same check cost 50 time units. The same applies to compaction. Our project successfully demonstrates the critical OS trade-off. Managing memory fragmentation is essential, but the cost of that management can itself become the new bottleneck. Our program has met all the project requirements from the object-oriented structure and interactive UI to the core functionality and most importantly, the correct simulation and analysis of these key OS concepts. This concludes our demonstration. Thank you.